we come to the second rule of thumb. This is using something called a vapor hazard ratio. So what we'll do first is define what this ratio is. The vapor hazard ratio is simply defined as the measure of a pure material's ability to volatilize, expressed as vapor pressure, divided by the material's occupational exposure limit, or OEL. So it's vapor pressure divided by OEL. And it was used in this relatively old paper by now by Popendorf in 1984. And so this particular paper defines this vapor hazard index as the log of the vapor hazard ratio. And also, I should point out that this particular reference does not address mixtures, but only pure solvents. So what is the reasoning behind using such a parameter called the vapor hazard ratio? The idea is that if two chemicals have the same vapor hazard ratio, they will require the same level of control to assure that exposures are not excessive. And so in some sense, the vapor hazard ratio is the Rosetta Stone of industrial hygiene. Well, first, just as in the case of the first rule of thumb, I'll go through the different steps and then we'll go through an example. So the first thing is to actually calculate the vapor hazard ratio score. So you divide the vapor pressure by the occupational exposure limit. And then the second step is to identify the required level of control from the vapor hazard ratio matrix. We compare the required level of control with the observed level of control. And then we need to make a decision. So if the observed level of control is greater than the required level of control, we say that that is a category 1 exposure. It's the lowest. If the observed level of control is equal to the required level of control, that's a category 2. But if the observed level of control is less than the required level of control, we basically call it category 4, meaning the exposures are exceeding the exposure limit. And this is a conservative approach to assessing exposures. And so you are always going to say this is a category 4 and not necessarily category 3, for example. So that's basically the rule of thumb for vapor hazard ratio. But then I have a fifth step. So what if the first and second rules of thumb give you different exposure categories? Then again, the use of conservatism in our approach basically mandates that we use whichever rule predicts the highest exposure control category. So we calculate the vapor hazard ratio. And I guess I forgot to mention this earlier, but the vapor hazard ratio is the vapor pressure in units of millimeters of mercury divided by the occupational exposure limit in units of parts per million. So we need to be careful about using the units correctly. So if the vapor hazard ratio is less than 0.05, then on the VHR scale, it's category 1. And the required level of control for this kind of a setting is that you need some general ventilation, roughly 3 to 6 air changes per hour. If the vapor hazard ratio is between 0.05 to less than 1, that's the second level in the VHR scale. And this means that we need the required level of control is good general ventilation, meaning 6 to 12 air changes per hour. And this is denoted by the acronym GGV, good general ventilation. If the vapor hazard ratio is between 1 and 25, then we need good general ventilation with capture at the emission points. If the vapor hazard ratio is between 25 and 500, then the required level of control is we need capture at the points of emission with containment wherever practical. If the vapor hazard ratio is between 500 to 3000, then we need containment. And then if the VHR is greater than 3000, we need primary and secondary containment, meaning it's very, very toxic and volatile. So As you can see, very small vapor hazard ratios imply that the vapor pressure is small and the occupational exposure limit is large, meaning it's not particularly volatile and not very toxic. And so you can get away with a very benign level of control. So good general ventilation or good general ventilation. As vapor hazard ratios increase, meaning that the vapor pressure increases, so it's more volatile, and the occupational exposure limit decreases, meaning it's more toxic. And so we need more stringent levels of control. So again, I'll go through these different steps one by one. So the first step is to calculate the vapor hazard ratio. So we divide the vapor pressure in units of millimeters of mercury by the occupational exposure limit in units of parts per million. And then we go to our vapor hazard ratio matrix. And let's assume that for a particular scenario, the vapor hazard ratio is between 0.05 and 1. So we require good general ventilation, or 6 to 12 air changes per hour. Then we, in our walkthrough, in our basic characterization of the workplace, we identify the observed level of control. And then we say, okay, is the observed level of control greater than the required level of control? In that case, the predicted category, exposure category is 1. The observed level of control is equal to the required level of control. The predicted ECC is 2. And if observed level of control is less than the required level of control, the predicted ACC is 4. And we compare, as a fifth step, the uh, predicted exposure control categories from the rule of 10 and the vapor hazard ratio. And if they are the same, then great. But if they are different, then use the highest exposure control category as the decision category. So in this slide, I'm showing chemicals that are in the same vapor hazard ratio category. And they don't necessarily have to be in the same family. So this is, for example, in scale 4, ammonia is an inorganic compound, benzene is an organic compound, but they both are volatile substances. And what this means is that both of them require the same level of control. So in this slide, I show some examples of various chemicals and their vapor hazard ratios and their required levels of control. So MEK, methyl ethyl ketone, has a vapor pressure of 86.7 millimeters of mercury and an occupational exposure limit of 200 parts per million. So we can calculate the vapor hazard ratio as 0.42, and this is in the second category on the VHR scale. And it requires good general ventilation, or 6 to 12 air changes per hour. And if you don't have that, then basically you can assume that you will have a category 4 exposure. Uh, Second, we have methylene chloride, which has a vapor pressure of 430 millimeters of mercury and an OEL of 25 parts per million. So the vapor hazard ratio is 17.2. And so this requires good general ventilation and capture at the emission points. And so what it means is if you're going to be in a factory that is producing methylene chloride or is using methylene chloride, then the factory requires this level of control for methylene chloride. And if it doesn't, then it means that you're going to have overexposures. The third one, hexachlorocyclopentadiene, has a vapor pressure of 0.06 millimeters of mercury and an OEL of 0.01. And so the vapor hazard ratio is 6, and it requires good general ventilation with capture at emission points. Uh, Finally, we have benzene. The vapor pressure of 95.2 millimeters of mercury and an OEL of 0.5. So the vapor hazard ratio here is quite high, 190. And so we need capture at the points of emission with containment. So we can see in this list that we range from methyl ethyl ketone, where the vapor hazard ratio is relatively small, 0.42, all the way up to benzene, which is not only very toxic but also very volatile, and we have a vapor hazard ratio of 190. And so the required level of control for methyl ethyl ketone is just good general ventilation, whereas the required level of control for benzene is you need capture and containment and so on. How can we use this concept when we are making decisions about exposures? So let's assume that you are in a plant that would like to purchase cyclohexane for a process at 25 degrees centigrade. And cyclohexane's vapor pressure is 96, its OEL is 100 parts per million, and the process ventilation is at scale 3 on the vapor hazard ratio. So we need good general ventilation with capture at emission points. And so if the plant manager comes to you as the industrial hygienist and says, "Is this okay? Can we buy and use cyclohexane in the facility without any changes to the facility? Will the exposures be acceptable?" You can take out your vapor hazard ratio, calculate it as 0.96, which is on the border between scale 2 and 3. And so the controls are adequate, and the exposure control category will be a category 2. And so you are going to be just fine. So that's the first example. The second example is that now let's assume that the plant has a good exposure assessment illustrating that the cyclohexane exposure is 25 parts per million, or an exposure category 2. And now the plant would like to use methyl ethyl ketone in the process. And what would MEK's exposure level be, and what it would be its exposure band? And so we know from my previous slide that the vapor hazard ratio for methyl ethyl ketone is 0.42, meaning that the controls would be more than adequate for methyl ethyl ketone. And the likely methyl ethyl ketone exposure can be estimated using the ratios of the vapor hazard ratios. And so we know the vapor hazard ratio for MEK and the vapor hazard ratio for cyclohexane. We find its ratio, and we then multiply it by the ratio of the cyclohexane exposure to the OEL of cyclohexane, and then we multiply it by the OEL of methyl ethyl ketone. So the cyclohexane exposure is currently at 25% of its occupational exposure limit. And so the MEK exposure using the above equation can be estimated at roughly 22 parts per million. And so the MEK exposures would be at the low end of exposure band 2 or exposure control category 2.